Hey everybody, I'm here to talk a little bit about some of the code that we find in lab number 6. Remember, you don't have to do these lab assignments, but I do want to go over the material and the code as a way to get you a little bit of extra instruction on some of the topics that you're working with on the homework. This first one is for time series with ARIMA. That's what would have been in lab 6. I believe there's at least one question on time series on homework 4. So in the first analysis, we're looking at a data set measuring drunken public arrests. And these are kind of classic time series data set that appears in a lot of textbooks. These come from Minneapolis public drunkenness arrests. They go from January 1966 to July 1978. And the reason why these are good to examine is that there was a change in laws around public drunkenness that ended up greatly reducing the amount of arrests, as we'll see. The first thing I did here is I just did a graph of arrests by month. You see people talking a lot about what are called seasonal factors in time series. We're really not going over seasonal factors, but it is something that bears a little bit of a mention. One thing we can see, and this isn't the greatest graph, but one thing we can see is that there's some months that have more arrests and some months that have fewer arrests. And I actually made a better graph here by putting labels on it. And again, I'll be posting this code in case you want to do that. I just changed the months which are represented in numbers to their names. And now we can see a little more clearly when the arrests are happening. One thing that we see is that there's kind of a big drop, November, December, January, and February, far fewer arrests than the rest of the year. And that's what we would call a seasonal effect. There's a reason why there's fewer arrests during those periods for being drunk in public. It's because it's really cold in Minneapolis. It's gonna be freezing there at many of these periods of time. So people would tend to be out less, that's reducing the arrests. Anyway, useful just to get a look at the data to start with to see if you see any obvious trends. The next question, here we're graphing arrests over time, and this is each month as a unique time period from 1966 to 1977 or so. One thing to note here, the new law was implemented at month 67. So if we look at this graph, you can see, right, there's a big jump. We went from a lot of arrests to a lot fewer arrests. And that happens right around the time that the law was introduced. You see that big drop. So what we're gonna do with ARIMA is try to address whether we have a statistically significant time series effect once we take into account autocorrelations and all of those additional assumptions. So the first thing I did is I predicted arrests from law using basic regression. Again, I probably wouldn't start with this, because there's limitations to the regression approach, but it's a nice in to show what we're doing with ARIMA and how that's just an extension of everything we learned when we were talking about multiple regression. So the first thing is, using the Durbin-Watson statistic, do we meet the assumptions regarding the absence of autocorrelations? Remember, the Durbin-Watson statistic is one of several ways that we can address the autocorrelation assumption. Again, autocorrelation assumption refers to the assumption that what's happening in week 1 is unrelated to what's happening in week 2, or technically it's that the residuals for those weeks are not related to each other. Since we're measuring things over time, there generally does tend to be some correlation there. But we want to test that assumption. There's a number of different ways that you'll see people test it. One way is the Durbin-Watson statistic. So to get the Durbin-Watson, I just run our basic regression analysis, and you can see here we've got law pre-post with the increased penalty for drunkenness. There's a negative slope there suggesting that yes, when they increased the penalty, the number of arrests went down. They went down by 439.6 arrests per year. Very nice having a categorical predictor in this, and that you can really directly compare what the effect of that intervention was. Now, this is statistically significant, but again, we need to address, before we address whether it's statistically significant, we need to address whether we've met the assumptions that underlie time series analyses. And one thing we can see is if we plot this using, our old regression assumptions, we'll see generally that we're going to have violations of that assumption. You can see we've got some homoscedasticity issues. The left-hand side is much more cleanly, much more clustered than the right-hand side, where there's a lot more variability. So we wouldn't meet our basic regression assumptions anyway. And we can see maybe some normality issues and the like. So next I used the package LM test. LM test has a function for doing the Durbin-Watson test called DW test. There's probably other packages that have this function as well. That's just the first one that I learned to use. With the Durbin-Watson test, it gives you a value and it gives you a significance. The DW value itself is not really important. It's on a really weird scale, so I wouldn't worry about that. I would just look right to the p-value. What we want here is, if we've met the assumption, we would fail to reject the null hypothesis. That would mean that there was no residual autocorrelation. Here, the probability is very, very tiny, 3 with about 8 or 9, with 9 the zeros in front of it, so well below a 0.05 criteria. That tells us we have violated the assumption because we're rejecting the null hypothesis here. Remember, generally with these tests, they give you a significance test on assumptions. Not rejecting it is consistent with meeting the assumptions. Rejecting it is consistent with violating assumptions. Another strategy we talked about, and probably the best strategy for doing for testing for autocorrelation issues, is using an autocorrelation function, or ACF graph. And there's a strategy that's attributed to someone named Pankrantz, wherein we want about a 1.25 ratio between the autocorrelation and its standard error, basically a t-value of 1.25. So we want below that for our first 3 autocorrelations, and then for the subsequent ones, with subsequent being, a vague number, no real value, numeric value put on that. For most of the subsequent ones, we can use a relaxed criteria, which is 1.6. And you can see the code here. The command is ACF. We just run that on the residuals from whatever our analysis was. The confidence interval piece, that's where I'm getting that bounding of 1.25. That's technically a 79% confidence interval. Not a value we normally use, but that's consistent with a t of 1.5. What we're looking for are values that pop above these dashed lines. But one thing to keep in mind is that this very first one, for some reason, this function graphs lag 0, which is something correlated with itself, which is why that's always going to be 1. So you can ignore that very first one, because that's never going to change. It's always going to be 1. Then we can see for the next 3 values, this one, and this one, that those are all well above those dashed lines, suggesting, yeah, we got some problems with autocorrelations, at least on the first 3 autocorrelations. There's some subsequent problems down the line using this criteria, but these down here, those aren't subject to that 1.25 criteria. Here we use a 1.6 criteria that corresponds to a confidence interval of about 89%. Then we can see for those subsequent lags, oops, these here, we've got one that looks a little problematic, that fourth one, but we'll have to see what happens after we start to make some adjustments. Remember, once we've violated these assumptions, we go in and we do this process where we add autocorrelative terms until we can reduce these residual autocorrelations down to a point where we're meeting or at least approaching the assumption. Another test here, the Box-Lung test. Box-Lung is a kind of a cumulative test. If you say lag 1, it'll do just the first lag. If you say lag 2, you can see the degrees of freedom on that went up. What that means is it's calculating this cumulatively for the first and the second lag. Lag 3 gets 1 through 3. A lot of people use this test. I think it's probably a little too liberal in that it's cumulative, and it may, if you have 10 lags, only one of them is problematic, but it's say the first one, and the other 9 are fine, it's probably going to come up with no problem, where you actually do have a problem. So I include Box-Lung because I know it's commonly used, but I would say that the autocorrelation function graphs are probably your better bet in terms of addressing assumptions. So you can see all of these, they all are significant because we had some serious issues. Big issue here, we can't use regression here. We're going to need to make some sort of adjustment to account for those residual autocorrelations. And that's where we get into using ARIMA. ARIMA stands for autoregressive integrated moving average. We're just working with the AR, the autoregressive piece. If you take a full semester course on longitudinal methodology, you would get into the integrated and moving average and seasonal components. We're only doing a brief overview here. So first up, I'm going to use the package forecast. There's many packages for doing time series. I just learned with forecast. So a couple of things. First, I changed the law pre-post variable to being numeric. Seems to work better with the forecast package there. And the way I'm labeling my models, fit 100, that indicates the different terms. There's a P. The first term is for the autoregressive component. The second term is the integrated component. The third term is the moving average component. Those last two, since we're not dealing with them, we're just going to leave them at zeros. So this would be P equal to 1, as that's generally noted. That is one autoregressive term. The basic idea is that we run the model. We don't really even look at the model. We first test the assumptions, and if we don't meet the assumptions, we go back and add another autoregressive term. So just keep popping in more until we get where we're going. You can see the format of this command is ARIMA, name of the dependent variable, comma, xreg, which tells it what the predictor variable is. In this example, it's just one predictor variable. At the end, I'll talk about how to implement multiple predictor variables. And then order C100, that's where we indicate the different terms. It's just that first number that we're going to be changing because that's the autoregressive piece. See, again, I've done my graph. And one thing we can see is that the first autoregressive term is now just about within where we wanted it to be. That's not surprising because we added one autoregressive term. We've reduced the size of the second and the third, but those are still, kind of popping up above those criteria. So I would say that based on just that, we haven't met the criteria. You can see the second part here. Nothing really much to see here because we've already rejected we've already not met the assumptions. The criteria for this second set of graphs is relaxed. It's a 1.6 ratio, as indicated by those little, by the dashed lines. And you can see we got one maybe down the line, maybe month 6 or so. That seems a little problematic, but that might go away once we account for more autoregressive terms. So next up, I went to a second autoregressive term. Basically, everything stays the same except for this one value right here. Now we're already adding a second autoregressive term, and I just labeled that as fit 200 or 200 to indicate that. We can see adding that second autoregressive term, we're looking pretty good, except for when we get to that third lag. Remember that first one, that's lag 0, can just be ignored. So that third lag seems a little problematic. And then looking down, we still maybe have some minor issues, a minor issue over here with month 6, but well, we can talk about that when we get there. So one thing we saw, we're getting better. These first two autoregressive terms look really good. They're almost 0, but this last one, this third one here is still popping outside of the range where we want to see it. So in this case, I'm going to go to a third autoregressive term. And one thing we see, once I dump that third autoregressive term in there, we have reduced these three, the first 3 values, lag 1, 2, and 3, we've reduced those to well inside that range. See what's happening with the subsequent ones. And with the subsequent ones, we have, now here's where you got to use a little judgment. We have one that's popping above over here at 11 months. And here's where, I usually say, okay, well, is there any reason for January to be correlated with with November? Is there any reason for months that are that different to be related to each other? And the answer probably is, there's probably no logical reason there. It's probably just noise. So when I get something that's really far down the line like that, I say, okay, well, I think we're probably good rolling with what we have at this point. Again, looking at Box Lung. Box Lung tells us that we meet the assumptions, not surprising. It also gives us p-values that are close to 1, which is saying, hey, look, it's almost perfect. And you can see no matter how many Box Lung terms I add, we're still good. So best model here, I would probably go with 3 autoregressive components, depending upon what criteria you're using. Some people might go with 2, but I like 3 in this case. And then now I want to take a look at our model. And one thing that I did is I extracted from the model the t-values and the p-values. Remember when ARIMA gives you output, it just gives you the coefficient and its standard error. We can get those using this code here, and it gave me my t-value, the probability value. Those are coming in a little bit weird here, but we can see that our beta, so not our beta, it's our slope was -407, meaning that we can say arrests were reduced by about 407 when we changed the law. T-value is 13, that p-value is 0. Obviously, we never report a p of 0, so we can fix that and clean that up a little bit. And as a little bit of a bonus, I want to show you how I wrote this using R Markdown. So I grabbed the coefficient, I grabbed the t-values, I grabbed the probability, and then over here, you can see the sentence in a ARIMA model with 3 autoregressive correlations. I just write that into Markdown. And then in line, I use asterisks to create italics around things. Say B is equal to, and we've got these little dash marks. R is telling it, okay, take something from R, and what are we going to take? We're going to take the value for coefficient. That's this value right up here. It's going to take our regression coefficient. And then for the t-value, it's going to grab the t-statistic. The p-value, it's going to grab my p-value. And I cleaned it up a little bit here by rounding these values so that I get the correct number, so I don't get p of 0 or my coefficients to 50 decimal places. And then when you knit in your Markdown, it will render to this. You can see the B, the T, and the probability. One thing that's nice about writing this way is that you can insert this directly into papers right from your output without having to copy it. Instead, it takes a little bit of time to learn that. Hopefully, we'll have a presentation on Markdown where people talk more about using these functions to write out analyses. Multiple predictors. I just added this today. I saw Doug had a nice post on Canvas working out a solution. A couple of ways to do stuff on ARIMA. I like Doug's version a lot better than I like my version. Just as an example here, I added a second predictor to our ARIMA. You can see that when I added a second predictor, what I have to do is I have to use this command called cbind. What that means is it combines my 2 predictors, and it's just the first predictor comma the second predictor. You can have a list as long as you want here. When I get output, you'll see that I've got output here. It's got X regression 1, X regression 2. Those are the 2 predictors in the order that they were entered. One thing I don't like about this is how they're labeled. We can see clearly the law prepo, the big one, it's pretty big, whereas the second one, month, doesn't seem to have much of an effect. Now, the solution that Doug provided was to create a list of, create a file with the predictors in them only. And the way to do that is using the select command in dplyr. The first thing that's added here, that's the name of the data file. And then the two predictor variables are listed next. And then this is forced into a data matrix. Once we force that into a data matrix, we get something called PREDS. And the forecast package can take that as a list. It has to be in a matrix form for some reason. Some of these packages are really fussy about the form that they get stuff in, but here we're predicting it. We're predicting adjusted from this list of predictors called PREDS, and we get the same results. But what I like about this is that it labels them as law, prepo, and month, so we don't have any confusion over what variables we're talking about. All right, that's about it for the material that was found in Lab 6. I hope this is helpful for the final homework assignment. I'll be posting, as always, I'll be opening the lab review up on Canvas so that you can reference it, so that you can look at some of the stuff that we went over. All right, I hope everyone stays well.